Well, you may find it beneficial. There are two opposite directions, fashions of simulating this mechanism. One is creationism and another is evolution. So if you want to process evolution, you don't need to change anything, you just run formalized molecular dynamics for eternally long, expect until immediate fraction happens. I don't know about Russell, but Braden selected research methodology inspired by creation. He creates specific initial momentum so that the reactant bumps into catalyst impact. It's somewhat larger amount of work, but higher chance of success. Just approach him from behind and go for insights. Okay, and who we are and what do we do? Oh, have you done your taxes?
2 months ago.
Month ago?
Months.
He was so organized.
Okay, as soon as I got my W-2, I did mine.
It's still half of a day.
I wonder if Braden's doing that right now, because I know he said he still has to do his. I don't actually know. I'm waiting for him to respond.
So.
The first time I did my taxes, I waited until like the last week, of course, because I didn't think anything of it. But the government had my birthday wrong.
Huh?
The government had my birthday wrong, so I had to go into the whatever it is in downtown St. Paul and fix it because they had my birthday wrong.
Oh man.
Is it fixed now or you still? You can celebrate it twice
They were just a day off, but like it was enough that they wouldn't accept anything. So
That's one case, so you could get an extension on your taxes.
yeah, I mean, I had it done, like I got it done still, so like that ended up being okay. But it was just like I was so confused because I thought I messed up.
This is why we follow Europe and how they do taxes. They basically just send you a form and you basically say,
Oh,
yep,
Switzerland. Switzerland does that. They do all your taxes and they'll send you a form and then you will look it over, and if there's something that you need to change, you just change that and resend it to them. If there's nothing to change, you just reset it and you're done.
That's so smart because people are way too dumb.
You watch the Adam Ruins Everything on that?
What's up?
Adam Ruins Everything did that.
I haven't watched it.
He was talking about the whole system and why we don't do it that way is because of lobbyists. Because tax firms make so much money off of, or not, accounting firms make so much money off of taxes that why would you start doing that? You lose billions of dollars. So they lobbied.
So our main goal is to complete research projects and do decent reports that will eventually serve as seeds for papers that you need for success of your career. And in the lecture time, you just relax and time to tell you with something related to the course. So what I'm going to tell is related to TD-DFT, which is important for your academic career, but you can survive in the course without running every single time. When you may need TD-DFT and how to run it. This is 5-minute thing. You just in Gaussian you select TD instead of ground state, and you select the number of excitations that you want to cover, and then you just submit a job. And then there are scripts that on one of the remaining labs I will share to extract things that we do need for what is the goal of TD-DFT?
Oscillator string.
Yes, and
Density matrix.
Absorption.
globally correct, but and in order to get absorption, you need oscillator strength and transition
Dipole.
energies.
Oh.
So when you run TGDT, it does generate transition energies and oscillator strength for each transition, right? And you do spectrum and become happy. But the theory is hard and it is worth of learning, so that if you ever include it into your research, you will know how to explain it in methodology section of your paper. In this course, you can't write without TDDFT, but if you want to include it, you may run it. When you characterize before and after reaction of thermal motion, so you can take your molecule and run TDDFT and look how the spectrum looks like. And if TDDFT spectrum differs from your independent orbital approximation that we do in GASP, it means that independent orbital approximation is bad. If it coincides, it means that independent orbital approximation is good. In many practical cases, the spectra computed by these two methods look the same in the shape, but they are offset by the certain energy. So TDFT gives typical small exclusion. It's not a rule of thumb, but it is normal. You get excitation energy less than just energy of light. So this is all stuff. So let me go find the thing with space and of using I was doing taxes and a quarter of a proposal, and well, it was only half an hour for the slides. Okay. Stop. Whom? Oh, stop here, probably. It looks like stop me. Hold me, stop me from talking. Stop me. Okay. So, ideally, this course was originally designed as extremely higher top level of the graduate curriculum. So you learn everything and only then this course. But there is no reason, because all practical things that we do in the lab do not need any of complicated things. You can learn them quickly. But there is one concept that those who are in physics may have heard about, and those who are in chemistry may or may not be exposed. So if you were, or if you will be in Chem 1, you will learn that there is quantum theory. There are different potentials, different models. Now, here we have very complicated, and they are not possible to solve analytically. But there is a like handful amount of problems that quantum problems that can be solved analytically. Hydrogen atom is the most complicated one. There is like box, free space, rotator. That's it. Free space, box, rotator, oscillator, hydrogen atom. Right? So there are only the 5 problems that you can solve exactly. All other problems are solved approximately certain level of accuracy. And right now in this course we do have programs, scripts, software that solves problems for us when it's energy state. But if you live before like 1965, most likely we will never see computer facilities in our life. And if you need to do science and compute something, it means abacus or pen and paper equations. So there are approaches that allow to find approximate solutions. when the exact solution is not available. And one of this class of tools is known as perturbation theory, where you compose you represent your problem as a exactly solvable one plus little addition, little perturbation. And there is a theory similar to Taylor series in idea that you can get orders of corrections that bring you closer and closer to reference. You can look without it, but later on you may see it. So TDFT is implementation of such theory. There are at least two brands of perturbation: time independent and time dependent. Same as perturbation. And TDFT originates from time dependent perturbation theory. I don't know if equations are needed. Probably not. So solution without perturbation and correction plus many orders of correction. And when we focus only on the correction that brings us closer to correction. Time dependent means that perturbation is not in the shape of potential, but from external oscillating field, oscillating or some other time dependent field. So, and the correction, just need this boil. Your success in Orbital. So this perturbation depends on the eigenstates of the absence of perturbation times frequency of oscillating factor from external field times unknown coefficients. So there are coefficients that tell how much each of the basis states is perturbed due to external oscillating field. So it was summary of the future. If you can take advanced point. So how does it project onto our molecule that is being exposed to oscillating electric field? A molecule that we have already described with ground state density function. So we do have two things that we may want to connect. One thing is Hamiltonian that is composed of unperturbed Hamiltonian when the molecule is standalone without any lasers flying around, plus low intensity field. H0, which is time independent, plus H prime, which is because of the oscillating field. And absolute value of this H prime is assumed to be much smaller than absolute value of H0. So due to, which means that your electrons sit around your ions, but due to oscillating electric field, they are either collectively oscillate as you see in plasmonics, plasmonic metal particles, or they experience transition to excited states. But very small fraction of overall electron density. So the question is to see the response of electron density to this external electric field, right? Good. And there is an expectation that if we expose our molecule to electric field, there will be overall density will be composed of whatever was before perturbation plus a little part, this one needs to be small, that will oscillate with the same frequency as incident field, because all other frequencies will relax with time. if this is infinite, started infinite time ago, it goes on infinitely forward to CW excitation. Little little contribution to the overall density. Okay? I want to appeal to your scientific intuition, especially if you did run TDDFT. Only Elisa? Anyone else? Okay. So, and everyone who did spectroscopy. Do molecules respond to any frequency? Or they have some favorite frequencies at which they absorb light?
They have certain frequencies.
Yes. So the change of the density in our density function framework, so this little induced change of the density will depend on frequency. Okay? So if you want literally follow what happens to density, it will be time dependent. But if you want to see amplitude of this time dependent thing, it will be higher if it is resonant excitation and it is small with off-resonant excitation. So the actual thing that we need to find is not time dependent but frequency dependent. So in some sense, we need to find transition density as function of incident light frequency. Okay? Why? Why we are not happy? Why we need to find it? We are skipping a lot of derivations. This is beautiful theory that many people like to derive, but it would take 10 lectures to go over details. So why do we need the density? I agree, we do need those frequencies at which this density maximizes, right? If you scan the frequency, this density will, as function frequency, will have peaks. And we need this frequency as resonance. But why we need it? This transition density will be an intermediate quantity to compute oscillator strengths for transition at given frequency. So we needed 4 oscillator strengths. And we also need to check which of these frequencies will be resonant. Okay. So what were we doing last time? If you remember. And I skipped the detailed review. What do you remember from Thursday meeting, if you remember anything? That's fine. It's so long ago. Any of you went to board deriving something? It's my favorite, otherwise you would remember something. Anything that surprised you by being too short or too expanded? Any matrices?
You talked about the density matrix.
Yes. Okay. So you remember something. You just pretend that you do. So the density matrix is the set of coefficients that convert orbitals, density for a given orbital, into density of overall electrons in the whole system, right? Coefficients at which pair of orbitals contribute to the overall density. And we can split it on 4 segments. The one corresponding to occupied at 0, originally, the one that corresponds to originally unoccupied, and transition density. And we got some arguments that at lowest order we need only the transition density. So the TDDFT theory tells how these transition densities can be found if we know something about the incident light. So how to find ability to your molecule correspond to incident light. And the transition densities are stored in form of vector. And if you skip several meetings of derivations, there is an eigenstate equation that if it is solved, it generates eigenvalues corresponding to transition energies and eigenvectors corresponding to transition densities. Equation. Values. Energies. Omega sub I. Eigenvectors. Transition densities. X sub I, Y. No one objects. Means everyone supports. No, I enjoy drawing this picture. So, although you can survive without TDT, you would feel much better if it is in your baggage. And practical aspects of running TDT calculation is very simple and minor. You don't need this course to run. But in order to discuss it and defend your findings against reviewers or aggressive attendees of your poster or oral presentation, you may have some ideas how it works and what it represents. So I'm talking about nothing except TDDFT, but it is very rich area. It is heavier than the whole course before it. So let me approach it from one specific aspect. How do we think about excitations? What is excitation? So before, up to now, we were speaking in the highlighter to be thicker. Orbital representation. There will be alternative so-called excitonic representation. So in our career in this course, we used to have highest occupied -1, lowest unoccupied +1, and many other states, right? And then we used to have energy. We used to have transitions. So first excitation has energy of orbital, energy of LUMO minus energy of hole, right? Second excitation, as it is drawn here, can be energy of LUMO minus energy of hole minus 1, right? Pair of orbitals. The first, second, third one will be here from energy LUMO +1 minus energy home. Okay? And the last one available if you do not draw more orbitals, number 4 will be energy LUMO +1 minus energy HOMO minus 1. Right? So you have 4 transitions. 2 occupied orbitals, 2 unoccupied orbitals, 2 times 2 times 2 times 2 equals 4. Consistent picture. Everything is clear. Listen. Does this picture agrees with TDDFT? Daniel, does this picture agrees with TDDFT? What you see when you calculate it and when you draw the spectra?
I want to say no. Because
Yes, very good.
Okay.
Continue.
Because you can't tell where it's going and where it's not.
Yes, it tells transition energy. It doesn't tell where it comes from.
Yeah.
It gives only excitation number 1, excitation number 2. So in the TDDFT output, you do not have source and final. Your source is always ground state. And then, which is assumed that it does exist. And then you have excitation number 1, excitation number 2, excitation number 3, excitation number 4. So excitation number 1 is just going from ground to first excited, without specifics. Which, well, there is a background hidden stored information how it can be composed of orbitals, but it is not the major form of output. And from the point of view of thinking about spectra, if you do experiment of recording absorption spectra, you do not need to know about orbitals. You just know they're objectively. There is a transition of given energy with such intensity. That's it. But now you know that there is a correspondence. First, transition can be transition from lowest, highest occupied and lowest unoccupied. The second transition will be whatever we called it, from homo -1 to lomo. Third and fourth, right? So I do not know how to verbalize it in a nice language, but if you are describing your system in the language of TDDFT or any other excited state theory, you do not have orbitals, so initial and final. You have just standalone excitations. And this is excitonic picture, and this is considered to be more general, more applicable, and I will be very happy and consider this course successful when you find an aggressive reviewer or visitor to a poster. You will not be scared by transitions between these two representations. So sometimes you and your reviewer may speak on different languages, like you speak on pairs of orbitals and reviewer speaks about excitations or otherwise. So I hope this figure helps you to make connection and do translations between these two figures at the conceptual language. When we will go forward in this TDDFT theory, and when you will practically run it, or two of you are running it every day or every week, you can see that for each transition, there is a record of excitation energy, oscillator strength, and then there are pairs of orbitals that contribute to given transition. So main difference of excited state theory is that given resonant frequency, resonant transition is contributed by more than one elementary pairs of electron and hole. Sometimes yes, sometimes no, but at least this opportunity is there. I don't know about you. You look exhausted, but I'm very happy. This is, I think, really good summary. Yes. So, very approximately, deep energy difference in orbital picture corresponds to excitation energy of the first, second, third. If any of these orbitals are degenerate or nearly degenerate, it will corrupt this approximate relation. So it is only to have a systematic view on this translation. Yes.
So in real world, our orbitals do have degeneracies.
Yes.
So what exactly do we do differently when we have degeneracy there?
first.
I already told you a story about Oregon and fine lady who served as a secretary correcting my English. Did I?
Huh?
Or maybe not or you were not you either forgot or I forgot or to tell you, or someone was not here. I will answer a question, I remember. Once I was a postdoc in Oregon and I was not feeling myself comfortable in especially writing English, and I was seeking opportunity to get corrections to whatever I read, like abstract. And there was a very friendly, fine lady from maybe high society who served as a secretary to the institute. And I was like, would you please help? She said, oh yeah. And then she was very polite and didn't know how to tell it. She said, you know, it's generally good, but there are some words that are not used in society, community. What? Did I use any wrong words? And she was like hesitant, like, some words mean bad things. What? It means people who are not intellectually strong. What? Energy states are degenerate. Colin McKillop, if you're watching this video, it is about you. So, if you have degeneracy, then you have just many of these transitions, and they will be lined up one after another. But there are discussions in the community that superposition and simultaneous cooperative, constructive addition of several elementary transitions is somewhat different from true excited states which represent interaction between electrons and holes. So in addition to just including several elementary transitions in one resonant state, the TDFT theory, as we will see in a couple of slides, has specific tools to take into account interaction between electrons and holes and formation of bound excitons. Therefore, energy of excitation is typically smaller in this TDFT than energy orbital difference of the same system with the same function. So here is one of the main achievements of human civilization. It was not yet awarded, but it is really a strong thing. And we are missing pleasure of deriving this equation, but we just getting acquainted, same as Alice in Wonderland. Like pudding, this is class, this is equation. So this equation has form of eigenstate equation. Some matrix, some vector, some eigenvalue. So upon solution, one is getting the eigenvector and eigenvalues are excitation energies, and eigenvectors are transition densities. There are so many of those. We need some index that different from orbital energies. I know you may use Greek or capital. So instead of two indices for source and final orbitals, we will have just H bar omega capital. So we just count excitations, not pairs of orbitals. And for each pair of orbitals, for each excitation, there is a transition density. Transition density is needed in this purpose, to find oscillator strength. Okay? What else? Do you have any questions? Or just staring? Just naturally. There is no trap and trick in the question. we have already introduced what is x, what is y, what is omega, and you know from yourself what is 0 and what is 1. Any other symbols that you do not know in this equation? Any letters that are new for you?
The A and the B.
Yes. So what is A and what is B? I'm also curious. Huh? Well, let me just bring it up. So if you solve this equation in absence of electron-hole interaction, of absence of any Coulomb interaction, and, in order to solve this equation, you need to solve it on the top of successful solution of ground state density functional theory. So if any of the exchange, correlation, and Coulomb are absent, I'm removing them, but they are not zero in real life. Then the only non-zero term will be this occupied and unoccupied pairs of orbitals. So upon solving this equation formally, it will be a trivial solution. You will get excitation energy equals to energy difference of pair of orbitals. Okay, a trivial solution. But if the electron-hole Coulomb, any forms of Coulomb interaction are present, it will be changed to excitation energy and to the transition density. So you remember this notation. Christian was attending this meeting, and Fatima was attending. I don't remember anyone else. So it was on the break on Senegal conference in the lobby.
Oh, way
When
back
we,
then.
Excuse me, I'm there.
Oh! Yes, how can I forget?
I have no idea.
So what do this net? I can check what do this notation mean.
Okay, well, no, I wasn't there.
So it is Coulomb interaction. It includes 4 orbitals, right? If it is just charge to charge, then 2 pairs of orbitals coincide. But generally, there are 4 that may not coincide. First, second, third, fourth. So it's Coulomb interaction. And if 2 would be coincide, like II, AA, it will be just Coulomb attraction or repulsion between electron localized on orbital I and orbital A, right? If the indices are not coincide, it is exotic things of this exchange, which has negative energy and stabilizes chemical molecule, right? So X stands for exchange. And the letter C stands for London must remember because he was running around in the center of the class. X equals exchange. And C equals correlation. So different forms of actually, Alisa, you shouldn't decline your presence. You could tell, like, look at the next line. See, 1 over delta R is Coulomb, and here are 4 orbitals. So, different forms of Coulomb interaction are entering these indices A and B, and they are responsible for electrons and holes attracting and forming bondings. And since we are doing density functional theory family of theories, we do not compute these Coulomb integrals literally. Instead, we can take them as a functional derivative of the functional in respect to variation of density. And this trick allows this calculation to be somewhat quick and somewhat precise. Enough? More or less. Occupied, unoccupied. If you have steam for this thing, you can return to it and devote more time or do quiz or exam derivation. I doubt that you will. So, conceptually, this omega sub I is transition energy. But we also get transition density. I was promising you that transition density helps you to find what? I think that is needed to plot spectrum.
Oscillator string.
Yes. So the transition density allows to find oscillator strengths. Do you believe it? Or maybe you want to believe it, but you do not see connection. Does it sound natural to you, or not quite?
Yeah.
How do you find oscillator strengths in your past life? You find oscillator strengths through transition dipole, right? Ij equals orbital. This is bad slide. Phi sub I R phi sub j, or sometimes you use the letter C, right? And then transition dipole absolute value squared gives oscillator strengths. Objections? No. Yeah. No, that's J proportional d J absolute value squared. It is very close to the favorite subject of Hannah, who loves the equation.
That's right.
But now we do not have orbitals. So TDFT doesn't generate orbitals. It uses them as an input, but it doesn't give them out. Well, I'm not lying, but I'm simplifying. There is a procedure that allows to interpret and convert TDFT results in form of orbitals. This is called NTO, and those who played may even know practically how to do it. But
no one knows how to do it.
But NTOs, natural transition orbitals, they are just way to interpret TDFT results. It is not the outcome of the calculation. The outcome of calculation are only densities. And now we have question how to find observable the transition dipole based on the density.
So I had a question based off that. What's the difference between a hoto and a homo? I guess a luto. What's the difference between like a hoto and a homo and a ludo and a lumo?
So so instead of MO molecular orbitals, there is TO transition orbital. So there is a way to decompose density, transition density, back to single pair of orbitals in such way, in such pair of orbitals that would give the same transition density. The transition orbitals are not observed. They are even stronger abstraction than functional. But the densities, if you want to project them onto transition density, if you want to project them into Cartesian space, they are 6-dimensional. They depending on vector 1, vector 2. And 6-dimensional things are a little challenging for human to visualize. Therefore, just to simplify visualization, there is a procedure of decomposing transition density onto pair of orbitals, photo and Lugin. But they are not observables, and they are only two for interpretation. Enough?
Yes.
So, how to convert transition density into oscillator strength? Observe. Expectation value is equal initial orbital operator final orbital. Or alternative, it is equals to trace of the density operator times operator of observable. If you do not believe this equation, look back to your PKM1 if you took it, look forward to your PKM1 if you plan to take it. But there is an alternative way of finding expectation value of any observable. Instead of taking sandwich between initial and final orbital, one can take a density operator, multiply it by operator of observable, and take trace. This is product of two matrices, and trace is
The sum of all of the elements along the diagonal
yes.
of the argument.
Yes, yes. So if the operators are represented in matrix form, trace is a sum of diagonal elements. This, I just skipped derivation of this statement because it is very, very general and just believe me, it's correct. They are identical. Now, since Vijay are familiar, he is familiar with the concept of trace, you are invited to work to teach us a little example. Yes. So what are we going to see here? The transition density is reduced only to, well, overall density matrix is reduced only to elements in the vicinity of frontier orbitals. So occupied, unoccupied, and transition density matrix is represented only by one element and one conjugated element, right? So much simpler, only the little square. Now, the transition density operator, transition dipole operator, has nothing on main diagonal and is non-zero on the off diagonal. So the task of Vijay is to multiply these two very complicated matrices and then take trace of it. Can you comment what are you doing?
Yeah.
I anticipated he's
Yeah.
doing row by column, but who knows?
Yeah, so I'm taking, for this first element, I'm taking the top row of the first matrix and multiplying it by, or basically taking like the first element in the top row of the first matrix, multiplying it by,
So this one
yeah.
gets 0 and this time this is
Yep.
0.
yeah, and then you just take the
Okay.
sum of
Okay.
both of those products.
Okay.
And then likewise for the rest of the elements, I'm doing top row and the rightmost column, and then bottom row in the left column, and bottom
Okay.
row in the right column. Yeah, so then this one will just give the ho and ho, and then because there's a
Mhm.
0,
Okay.
and then yeah, this one will give ho lu. Oh,
That's fine. That's fine.
Yeah, so then the trace is just equal to d multiplied by this element and then this element.
Okay. Excellent. Let's applaud. So, do you see a discovery that Vijay just completed? I know I skipped several, or just skimmed through several introductory steps, but let's look how to interpret his result. So we claim that it is expectation value of transition dipole, and it's fine to have the vectors here. This will be matrix element between. Oh, okay. Let's keep it without indices. So the expectation value of transition dipole does depend only on the transition density elements. So here we started with maybe non-zero elements of occupied and unoccupied, but they do not contribute to the value of transition dipole. So for the practical purposes of computing the absorption spectrum, we even do not need to know the correction to unoccupied orbitals. We need only transition densities because only elements of transition density segments of overall density matrix contribute to expectation value of transition dipole. I was able to do it. So let me verbalize it. Transition density determines transition dipole. T, D, D, T, D. T transition density determines transition dipole. Right? So if you do know transition density, you know transition dipole. And you already know the transition energies. So you have all input information to compute spectrum. Right? And your transition dipole enters the oscillator strengths times I don't remember what is on the next slide, but it would be very reasonable to rewrite once again favorite equation of one. Yes. So this is old-fashioned. This is what we do with VASP independent orbital approximation. But if we run TDDFT, instead of two indices, we have one I capital, one I capital for oscillator strengths, and one transition energy for this for here, right? And these guys are borrowed from the output of TDDFT calculation. When we meet on Wednesday, the primary goal will be to catch up on the project. But if time allows, it will be very reasonable academically to illustrate quickly running something on TDDFT and analyzing, or just looking, getting familiar with extracting these two columns of data from its output. Some fraction of class is aware of this procedure. Now it would be reasonable either to summarize it or maybe to finish. Okay. So comparison of orbital picture and excitonic picture. In orbital picture, you have two indices everywhere, and excitonic picture you have one index everywhere, right? But you can run it for the same systems, and if the electron-electron interaction is not as critical for systems, if the electrons and holes are almost independent, unbound, this spectra would coincide. The benefits of the excitonic picture that it is much more reliable and accurate. It is critically needed if there is a formation of bound excitons for molecules, conjugated polymers, and pairs. Limitations. How many excited states can you run in TDDFT if you practice? Maximum number of excited states that you did run.
I don't know. I know I was like 125.
125. Excellent.
Around 70.
70. Okay. What is the number of excited states you can do with this approximate method? Actually, we do it all the time. In the file input overlap, you tell like use orbitals from 1 to let's say 200, with HOMO being about 100. So 100 occupied, 100 unoccupied, and you use all the pairs, all combinations. 100 times 100 equals
10,000.
10,000 excited states, and you do it in like a minute, right? So amount of excited states and range of energies to be covered by the independent orbital approximation is like a couple of orders of magnitude bigger than you can do with TDFT. TDFT will not scale. You will not scale and will fail if you request 10,000 excited states. So it's your creative balancing of these two approaches based on your needs. So if your system is huge, there is no chance to do TDDFT. If it is small and you need to defend that you computed everything precisely, TDDFT is your friend. Yes. Thanks for staying. I will stay here a little longer if you need to answer questions. And I anticipate that Christian may have a quick question.
I do.
You do.
Was that it? I don't know.
No. If I do have a question, it's not a question.
My brain's fried today.